So now that we've explored some of the specific pollutants, their sources, and the policy and legal frameworks for protecting our waterways from those pollutants, we can start to focus on the IDAH2O program. In each of the next 3 modules, we will focus on one of the stream assessments. Now, I like to start with the habitat assessment. It requires the most amount of time to complete, and some of the techniques require some interpretation since they result in qualitative data. The habitat assessment is conducted only once a year at times of low flow, like August or September. The stream's structure and habitat readily change only during times of high flows, so your descriptions will be good for the year. More of the banks are visible during low flow, and the rocks and other substrate in the bottom of the stream are more accessible at that low flow too. You can follow along in the IDAH2O handbook. You can also follow along with the habitat assessment form, downloadable from this module or from the IDAH2O website, and also located in the IDAH2O handbook on pages 25 to 28. You will use this form to document all of your observations. Remember that you will need your monitor and site numbers, a site description, and information about others who you monitor with. Now, if you check the stream unsafe or too dry to perform all measurements selection, the online form no longer requires all data points to be entered before you submit the form. As always, take some photographs. If you have a question about how to document something, take a snapshot, write down a description of what was confusing or how I can clarify the process, and send that to me once you're back into self-service. I'm happy to help you out anytime. There's no dumb questions. They're all good questions, and I'm here for you. All right, let's get started. There are 2 broad ways of looking at a stream. First, you can study the cross-section of the stream in a straight line from the top of one bank across the flow to the top of the other bank. This type of cross-section is called a transect. Here's a picture of a model transect. As a general rule, a scientist will standardize everything they do when collecting data. Many professionals will always start with the left bank, then move to the right bank. But which is which? Now remember, we are interested in the water flowing off of the landscape into the stream as it reaches your location. Therefore, you will be standing in the stream and facing upstream, toward the water that you are interested in collecting data. As you are standing in the middle of the stream, facing upstream, the left bank will be on your left and the right bank will be on your right. This is a different way of looking at the stream than, for example, a canoeist or a rafter who's floating downstream, watching where they are going. Now in that case, river left and river right are opposite our left bank and right bank, since our observational interest is different. The transect will start with the riparian area and or the floodplain at the top of the banks. The 2 terms are not interchangeable, but the riparian area and the floodplain can often overlap considerably. We will get into what a riparian area is in more detail, but for now, know that it's the shrubby area with grass, bushes, and a variety of trees along the edges of a stream. A floodplain is the area into which a stream overflows during times of extremely high water. The floodplain starts at a line on the uppermost part of the stream bank called the ordinary high water mark. This is a legal term defining exactly where the public access to the bed and banks of a navigable waterway start and end. And it is roughly defined as the line at which the land plants no longer grow due to the scouring action and inundation of the land by a water body. Above this line is the floodplain area where floodwaters will spill over the banks into the land. This line is also known as bank full. You can see that here on the image. Below this line is the bank, and eventually the bed of the stream. Determining exactly where the banks end and the bed begins is not important, but defining the ordinary high water mark is important. In some places, an identifiable deepest area is present as well. The technical term for this deep spot is thalweg, Thalweg. The thalweg is defined as the course that the stream retreats to when it is at its lowest water. In any stream assessment should be either in the thalweg or in the center of the stream, whichever is more easily identifiable at your transect. Now, the other way to look at a stream is to follow it for some identifiable length. This is called a stream reach. Professional stream assessors will use a standard length, for instance, 100 meters or maybe 1,000 meters. In mapping, a reach is often defined as the length of stream between two tributaries. In IDAH2O, the reach is defined less precisely. Instead, the reach is the length of stream that you can see something of its banks from standing on the bank at your transect. You can define the reach as you see fit, too. For instance, perhaps you are interested in the entire stream through your property. That can be your reach. Before you start gathering data, you need to identify the location of your transect as precisely as possible. We discussed getting the latitude and longitude coordinates in the last module. In a perfect world, your site location is in the middle of the stream directly on your transect. If your site location is actually on the bank of the stream at your transect, that's acceptable too. You don't have to have a precise measurement for your reach, but you will want to consistently monitor that reach as well as your transect. You will begin each of the three assessments by looking specifically at your stream's transect. At some point in each assessment form, there is a note that prompts you to broaden your focus to include the entire reach. In the habitat assessment, that switch happens after you describe the riparian zone and before you look at stream sinuosity. There are 4 major habitat types in a stream: riffle, run, pool, and glide. In a perfect world, any stream reach will have all 4 habitat types, but often reaches only contain 1 or 2 habitat types. Streams experiencing aggradation, for instance, might only have riffles. Your transect can be at any of these habitat types, but the professionals often prefer setting their transects at a riffle or a run since it's easier to complete some of the assessments. Riffles tend to be easier to access the substrate on the bottom, and runs are generally easier to gather stream velocity data. Pools and glides tend to be too deep to easily gather substrate data, and often they have at least one steep bank. A riffle is a more shallow, turbulent area of the stream where rocks protruding to or near the surface cause a lot of aeration and random movement of the flow. Often there is no thalweg present or evident. These areas often have high dissolved oxygen concentrations but offer little good fish habitat. Many of the aquatic macroinvertebrates like riffles for both of these reasons. A run is a smooth-flowing stretch of the river with fast-moving water but no turbulence. It is sometimes referred to as laminar flow because the stream is quiet but moving. There is usually a thalweg evident in a run, but not always. Runs can have good fish habitat, especially if there are overhanging banks with roots protruding into the river. Runs that are located below riffles may have high dissolved oxygen concentrations. A pool is an especially deep portion of the stream. These are sometimes the best swimming holes. Pools often form at the outside of bends and also can be formed below an obstruction like a log or ledge where scouring action carves out a deep spot. Fish especially like pools since they can be a refugia during times of hot weather. Cool groundwater seeps into these deep spots, providing a livable space even when the surface water is lethally hot for cold water aquatic life. Fine sediment can also settle into the bottom of pools, causing the bottoms to be comprised more of muck or silt. A glide is the most difficult to describe. It's the area below a pool where the bottom of the stream is trending upward, but the surface of the stream is trending downward. The current increases out of the pool through the glide and into whatever habitat is next, say a riffle or a run. Fish often lay their eggs in the gravels of glides, since fine sediments settle here less frequently. The eggs require good stream flow to provide oxygen, so avoiding fine sediments is essential. Glides, like all the other habitat types, provide unique opportunities for a wide range of different aquatic life. Now that we know the basic nomenclature for the different parts of a stream's habitat, it's time to begin describing the stream habitat assessments and the science behind them. Remember that if you choose to participate as a citizen scientist, you will have the opportunity to practice each of these in person in a representative stream during the field portion of the workshop. Therefore, I will describe each technique in minimal detail and instead will focus more on the science and the reasons for each assessment. The material that makes up the bed and banks of a stream will provide varying habitat for all aquatic life. What the stream bed and banks are made of and how locked into place the materials are provides a lot of information about the potential for water quality too. The Woolman Pebble count was developed by a pioneering fluvial geomorphologist, M. Gordon Woolman, in 1954. It is a statistically representative method for determining the size of substrates on the bed and banks of a river. Over time, distributions of particle size can be compared to see whether there is a shift toward finer sediments, which can smother fish eggs and cause other problems. Such a shift is a sign of increasing erosion from the landscape. It also informs hydrologists about how much energy the stream has. The larger the substrate is, the more energy it took the stream to roll it into that location. At high water, you can hear streams rolling huge rocks along with the characteristic click, click, clunk. You can read about how the U.S. Forest Service describes the Woolman Pebble count in a publication, the USFS Woolman Pebble Count document. It's available in this module. Now, IDAH2O uses a slightly simplified version. I'm first going to describe the sampling technique, and then I'm going to describe the sample measurement technique. Now, this takes a little bit of time to describe. It is, in fact, the one assessment technique that takes the longest, so bear with me. And remember that the technique is spelled out nicely in the IDAH2O handbook on page 19. You might want to follow along. Note, too, that this is one of two assessment techniques that's almost impossible to complete without a partner who is acting as a scribe. The Master Water Stewards should focus on picking up the rocks while keeping your balance in the stream. The person in the stream can call out the size class of each piece of substrate to your partner, who keeps tally of each sample measurement. You will start from the ordinary high water mark on the left bank, at or shortly below your transect. The first selection should be right at or immediately below the high water mark. You will work your way across the stream, one step at a time, until you have reached the high water mark on the right bank. In IDAH2O, we cross the stream at a right angle to the flow. If you reach the other side before you have measured the minimum required selections, which is 50 or greater, take one step upstream and return all the way across the stream to the left bank ordinary high water mark. By taking one step upstream, you ensure that your previous work does not interfere with the samples on your way back across. As the habitat assessment should only be completed at low water, the first few selections of substrate may be out of the water. These samples will be recorded as outwetted. Once you sample some substrate that is touching the water, your scribe will begin recording the sample as inwetted. Anytime you leave the water, for instance at a midstream gravel bar or the far bank, the scribe will again record samples as outwetted. To improve consistency of substrate selection, professionals will use some whiteout or acrylic paint or another method to create a little mark on their wader boot. They will select whatever substrate is closest to this mark without looking. You can do the same thing without the paint by focusing on whatever substrate is closest to, say, the tip of your big toe. You should attempt to do this without looking, though that can be difficult to keep your balance. It's okay to look, as long as you select only the piece of substrate closest to your big toe. Once you have completed the measurement of the size of each substrate sample, you will toss it downstream. By tossing the sample downstream, you eliminate the possibility, no matter how small, that you might resample the same substrate. Then, take a step toward the right bank and select another substrate sample. Note here that I don't say select another rock, as the substrate might be silt or sand. The distance of your step does not matter, as long as every single step is the same distance. Again, the idea is to be consistent so that you can complete a statistically representative sampling of the bottom of the river. So remember, there are 3 general rules to increase consistency and to ensure a statistically representative sample. First is that you must measure a minimum of 50 samples. If you get to the far bank and you have not counted 50 samples, you need to take a step upstream and continue back across. You can eliminate the second trip by measuring the slope distance of the banks and bed, dividing by, say, 51, and taking samples at that interval. It's not the straight line distance across the creek, but instead the distance as if you glued the measuring tape to the banks and bottom to determine the distance. Second is that you must complete a transect from ordinary high water mark on one bank to the ordinary high water mark on the other bank. You can't stop sampling in the middle, even if you reach your 50th sample. Third, the spacing between each sample must be about the same. That is, your steps should be the same length. On a big, wide stream, your steps can be longer than on a narrow stream. You should avoid looking at the rocks you pick up, as we are all prone to pick up the shinier one or the larger one. But again, since that is difficult to do while keeping your balance, it's okay if you are consistent about picking up the substrate immediately in front of your big toe. Phew, okay. That was the process for selecting a statistically significant, consistent sample set from the stream bottom. The procedure for measuring each sample starts with the ruler provided in each kit. It's called the Woolminator. Okay, it's a funny term, and I often use my best Bob Newhart impersonation when saying the word Woolminator. You'll use the Woolman's measuring tool like a ruler. Place the substrate sample, in this case, a rock, at the beginning of the ruler. Note that I'm not trying to fit the substrate sample into any particular area of the ruler. Instead, I place the rock at the line that marks the beginning, just as though that were the 0 centimeter mark. The small uncolored area between the 0 line and the orange VFP, which by the way stands for very fine pebble, is the width of the largest size of sand. Sand is defined as particles up to 2.5 millimeters in width. Anything that fits within that white uncolored part of the Woolminator is either sand, silt, or clay. You can use your sense of touch to determine which of these it is. Sand is coarse. Silt is much finer than sand, but larger than clay. It feels smoother to the touch. Clay is the smallest particle size and feels greasy or slimy to the touch. Now in IDAH2O, we only differentiate between sand and the smaller two, silt and clay. The size classes increase from there through very fine pebble, pebble, coarse pebble, very coarse pebble, small cobble, large cobble. Once a substrate sample exceeds the length of the measuring tool, you can just submerge it to measure how many lengths the substrate is. This avoids you having to pick up any big heavy rocks. When the size of the boulder exceeds 4 Woolminator lengths, it's considered a large boulder. Since your steps might be shorter than a boulder, you might sample the same substrate more than once. This is acceptable for these largest of substrate samples. The substrate samples are not perfectly round. Now, if this were the case, you would simply measure the width at any point. To ensure consistency and to measure the substrate's axis that is of the greatest importance, you will find and measure the intermediate axis. That is, avoid the longest size of an oblong rock, and also avoid the narrowest. Rivers roll substrate along the bottom based on the intermediate axis. Rocks don't tumble along the river along their long axis. The shortest axis isn't meaningful in terms of the energy it takes to tumble a rock along. It's the middle distance, or intermediate axis, that limits the size of the rock that the stream can move. Therefore, place the rock on the Woolminator and measure the middle distance, either in millimeters or centimeters, or according to the pre-measured size classes. The images on the slide and in the handbook will help you to understand that measurement. Embeddedness is the other assessment technique that describes the nature of the materials that make up the bed and banks of a stream. It refers to the extent to which rocks are covered up or encased with fine sediments. Rocks, gravel, cobble, etc., with lots of interstitial spaces provide good habitat for the little bugs and snails and such that live in the stream. Fine sediments like sand, silt, and clay can fill in these spaces, reducing the variety of habitats available and potentially smothering fish eggs. The observation is done directly under your transect. To estimate the percentage of embeddedness, observe the amount of the fine sediments found along the transect. If rocks are overlain and surrounded by a lot of fine sediments, if they cannot be easily nudged with your toe, then that percentage of the width of the stream is embedded. You will note the percentage of the distance across the stream that is embedded. You can tell a lot about the stream's long-term stability and about the aquatic life it can support by looking at the shape and condition of its banks. High, crumbling banks that look like walls are indicative of excess erosion and changes in the watershed's hydrology. Gently sloping banks with a variety of shrubs, grasses, and trees on the upper portions, or low, undercut banks with lots of vegetation growing on and through them indicate more stability and greater biological habitat. When the banks erode faster than the stream can rebuild them or carry away the sediments, aquatic life will be negatively affected. First, we will describe the stream's bank characteristics. Check all that apply from the list provided on the assessment form. Start with the left bank and then repeat for the right bank. A cut bank is eroding away quickly if there's no vegetation to hold it in place. Some cut banks are more stable with the presence of vegetation. Sloping banks are often found on the insides of bends, like here on the right, where the water velocity is reduced, allowing for sediment to deposit and slowing erosive forces. Sand and gravel bars, again like this one here on the right side of this picture, are often associated with these sloping banks. Riprap is described as big rocks that people place near road crossings and in areas with high erosion. These rocks are so big that the stream doesn't have enough energy to move. They are great for protecting property, but they're terrible habitat. Bioengineered solutions that provide bank stability and also habitat are the modern preferred method. Some streams have been moved or altered into a constructed channel. These banks are usually a steep, uniform slope, but because they are engineered to withstand the stream's energy, they usually exhibit little erosion. The other category is there for the rare exception to these types of banks. In the old days, people would send old cars, tires, other large debris over the edges of eroding banks to try to hold them in place. The stream usually finds ways to erode the banks around these objects because the real culprit is located somewhere else. Next up is determining the stream bank condition. Stream banks are either covered by vegetation or they are bare. Also, banks are either stable or unstable. A bare bank can be very stable. Most gravel bars are not eroding away. While stream bank vegetation can slow erosion, some vegetated banks can be highly unstable. Check the one selection that describes the left bank and then the one that describes the right bank. The stream channel shape describes whether the bank is sloping, vertical, or undercut. These are described as inverse trapezoidal for sloping banks, rectangular for vertical banks, and trapezoidal for undercut banks. Your assessment form has each shape described, so you don't have to remember the difference between, say, trapezoidal and inverse trapezoidal. Check the one selection for the left bank, then repeat for the right bank. Now it's time to look up and away from the stream itself. The tree canopy provides shade for the stream, which helps to moderate any warming of the water. It also slows down raindrops, reducing soil erosion near the stream. Tree canopy cover is distinguished from ground cover in that it is above your head. There are several tools that professionals use to quantify the canopy cover in a statistically representative way. One of these is a spherical crown densiometer. This is a curved mirror with a grid pattern used to look up at the canopy above. Any point on the grid on which open sky is projected is counted as a percentage of the sky that is not covered by tree canopy. Using that instrument, a precise percentage of canopy cover is calculated. Another method is using a solar pathfinder. This instrument uses a semi-reflective plastic dome that reflects any light that gets through the canopy. Under the dome is a graph that aligns with and displays the sun's path each month of the year. It's better for determining how many hours the sun will shine directly on a given point, but it can also be used to determine canopy cover. In IDAH2O, we use a simpler method. Simply look up and make your best estimate of the area above the stream that is covered by the canopy. Do that in 25% increments. I recommend using your cell phone's camera in the center of the stream, right at your transect, and point it upwards. The slide here shows 3 photographs. This one, greater than 75%. This one, up to about 50%. And this one over here, less than 25%. Just be sure not to drop your phone in the water, or do what I do and invest in a waterproof case for your phone. Okay, I mentioned riparian zones earlier, those brushy areas that exist along and adjacent to streams and ponds. They tend to be thick and brushy and almost impenetrable. People tend to not like them since they make it hard to access the stream, and they block the direct view of the stream. However, removing riparian vegetation results in stream bank instability and allows pollution to reach the stream from higher up on the landscape. Note in the lower right photograph where the bank is eroding badly in front of the two-wheeler track. You can see a piece of grass that's sloughed off the top of this unvegetated cut bank. That goes to show how ineffective grass or turf is at retaining stream banks. Now note the single little tree by the green arrow. That one tree is helping to hold back that entire bank. Its roots are holding the soil in place and allowing additional vegetation to grow around it. The difference is at least a couple of meters in distance. The bottom left photo shows one solution to maintaining robust riparian vegetation. The landowner here has used rail fencing to keep livestock out of the stream. There is some brushy areas adjacent to almost all of the stream. And note that the banks are not raw and eroding. In the event that a cow or calf finds itself on the stream side of the fencing, it is relatively easy to disassemble a segment of this rail fence and herd the animal back into the pastures. It requires a water source away from the stream, which in turn requires an investment in a trough, pump, pipes, power source, etc. But there are programs to help landowners afford such off-stream watering sources. In IDAH2O, we measure the width of the brushiest area right along the stream. Technically, the riparian zone can extend into the forest lands farther away from the stream, but we are most interested in the contiguous brushy areas, if there are any, that can also include grasses, sedges, forbs, and trees immediately adjacent to the stream. We measured the width of the riparian zone directly along an extension of the stream's transect in 3 broad increments, 0 to 5 meters, 5 to 25 meters, and greater than 25 meters. 5 meters is just a little more than 5 yards, which is about 15 feet. Start at the ordinary high water mark on the left bank and run your tape measure through the brush or estimate its distance in one of those increments to where the thick brush ends. Repeat for the right bank. Some places won't have any riparian zone, and that still fits within 0 to 5 meters. When you are measuring the riparian zone width, also note the percentage of that distance that is covered by various types of plant cover directly under the extended transect line through the riparian zone. Again, plant cover is what is covering the ground, not the canopy above you. The percentages of the various plant cover must add up to 100%. You can measure in centimeters or simply provide your best estimate in increments of 10%. Again, start with the left bank and then go to the right bank. Up to this point, we have been focusing on collecting data specific to your stream's transect. It's now time to turn our attention to the entire stream reach. Streams naturally meander across the valley as a response to the energy that it carries. Meanders slow the water down, reducing the erosive energy, and in turn increases the available habitat. Sinuosity is a measurement of this phenomenon. It's the ratio, or difference, between the straight line distance directly down the valley, directly from point A to B, and the stream's channel distance. A stream channel that is straight, with few bends or meanders, exhibits low sinuosity. Small, steep mountain streams, or streams that have been channelized, can have low sinuosity. Stream channels with moderate sinuosity have few bends greater than 90 degrees. A highly sinuous stream has a significant number of bends and meanders that make a greater than 90-degree curve. While rare in Idaho, some streams are described as braided. Braided streams are divided into multiple small channels, usually due to aggradation by an accumulation of coarse sediments within the bankful channel. Parts of the Snake River between Rexburg and American Falls Reservoir are, or should be, braided. For the K-12 teachers out there, calculating a stream's numerical sinuosity is a great math lesson for about the 5th grade and up. But for IDAH2O, we simply record sinuosity of your stream's reach as low, moderate, high, or braided. Within your stream's reach, you will likely find multiple microhabitats. Each of these provides unique living conditions for a variety of aquatic macroinvertebrates and fish. Your assessment form contains a list of microhabitats. Check all that are present within your stream reach. Algae mats refer to any large areas on the bottom of the stream covered by algae growing on the substrate. Large organic debris refers to any logs greater than about 6 inches in diameter. These larger woody debris enhance stream stability and habitat. Root wads are living plant roots in the stream, often found growing out of the stream bank, or stumps with roots within the stream. Both of these provide great habitat for bugs and small fish escaping predation by bigger fish or birds that can't get through the tangle of roots. Fallen trees, like organic debris, help stabilize stream banks and beds. It slows down sediment and provides habitat and cover for fish and bugs. Silt and muck, while harmful to some aquatic life, can provide habitat for other life, specifically benthic aquatic macroinvertebrates. Benthos is a fancy word for the mud at the bottom of a water body. Sand, too, can provide habitat for some aquatic life. I've found some types of caddisflies that specialize in living on sandbars and other sandy environments. Leaf packs are especially important to some aquatic macroinvertebrates. These are areas of densely packed leaves in the stream. You can make your own artificial leaf pack, place them in the stream, and return a few days later to collect and identify bugs that like that sort of environment. Rocks provide great habitat for fish and bugs. Weed beds are areas of the bottom that are covered in macrophytes, or larger plants rooted in the bottom. Undercut banks can provide complex habitat for fish and bugs and are not always associated with excess erosion. Overhanging vegetation provides shade, evapotranspiration that cools the air above the stream, plus opportunities for unlucky bugs to fall off and feed the fish. Finally, you might find objects like shopping carts, tires, old cars, and many other man-made junk in the streams. Record what you find by checking all of the selections that apply along your stream reach. If you find something that isn't on the list, add it under Other. Once again, the assessment form provides a list of many common land uses that might be present immediately adjacent to the stream. Don't count anything that isn't within easy eyesight from the stream's edge. In this case, we are concerned with land uses that are very close to the stream. I won't go into detailed description of these common land uses, as they are likely already familiar to you. Remember that land uses within a watershed can have a negative or positive effect on the stream, and that the effective implementation of best management practices will reduce any impact. Check all that apply along the stream reach. The final two techniques in the habitat assessment are to document human use activities that you witnessed while you were at the stream and the evidence of human uses, even if you didn't personally see them. The assessment form provides a separate list for human use activities and evidence of human use. Some uses will affect the stream more than others. Campfire pits right next to the stream can increase nutrient concentrations and increase pH, or make it more basic. Camping next to the stream can compact adjacent soils and reduce riparian zones, resulting in more erosion into the stream. Select all that apply to your stream reach from each list. Okay, that's it for the habitat assessment. Again, this is the most lengthy of the 3 assessments, likely taking 20 minutes or more once you're used to the techniques. But this assessment is only done once a year and at low water. Next up, the 4-question quiz for this module, and then on to module 5, the physical and chemical stream assessments, and that one's a whole lot quicker.